Hi everyone, I am Xutong Miao from Xi'an Jiaotong University and I'm honored to present our work. Dynamic Vision-Enabled Machine Condition Monitoring, a point cloud-based diagnostic methodology. Our work is supervised by Professor Li Xiang. This research explores a novel approach for non-contact machine fault diagnosis using event-based cameras and point cloud data. I structure my representation around three parts. They are overview, research methods, results, and impacts. So, in recent years, machine fault diagnosis has relied heavily on contact sensors such as accelerometers. These sensors attach directly to machines to detect vibrations and faults. However, they come with limitations like installation and maintenance costs, limited mobility and coverage, interference and noise. In contrast, we explore a non-contact alternative, that is event-based camera. Unlike traditional cameras, as you can tell from the video, event-based cameras capture only changes in brightness, a 2G pixel. Thus, they provide high temporal resolution and low latency. Additionally, they are flexible, economic viable. These features make them highly effective in contactless and real-time monitoring applications. The problem here is how can we transform this dynamic vision data into a format suitable for machine fault diagnosis? So let's look at the event recorded here. What is exactly event? Actually, each event is represented as a four-tuple element where T is the timestamp, X and Y are spatial coordinates, and P is the polarity of brightness change. -1 means brightness decrease, vice versa. As you can see, the dynamic vision data here has complex data formats, difficult feature extraction, and lack of established models to process. Specifically, our main contribution here is we treat event-based data as 3D point clouds, and we apply deep learning methods for accurate fault diagnosis. Next part is our research methods. So to obtain our data, we conducted experiments on a rotating machine. This is the general layout. And we have event-based camera here capturing data from 3 different angles under 4 conditions, like inner race fault, outer race fault, ball fault, as well as healthy condition. This is the visualization of our data from different angles. The reason here is we want to minimize the impact of factors like occlusions, reflections, or variations in the bearing's appearance from a single viewpoint. And since the cupola part exhibits a higher density of events compared to other areas of the task rig, so we mainly select this area as our main region of interest. Notably, to reduce the sensitivity of the analysis to the exact placement, different regions and time segments are randomly selected to form each sample. And our geometric transformation approach converts the event data, which includes spatial and temporal information, into a point cloud representation. This allows us to apply deep learning technique for fault detection. Here we follow the PointNet++ framework and design our sampling layer, grouping layer, and the PointNet layer. After 2 layers of such sampling, grouping, PointNet layer, the subsequent PointNet layer operates on the output, followed by a fully connected layer and a softmax activation function to give the final classification results. In summary, we use an event-based camera to capture raw event data from a monitored machine and convert the data into point clouds, extracting periodical and spatial features. After random sampling, we apply deep learning on the point sets for model training, and finally test the model for fault diagnosis. Now let's talk about how we evaluated our method. Our results were highly promising. We evaluated 4 tasks, combining different camera angles and rotational speeds. Across all tasks, we achieved an accuracy of over 85% to diagnose different fault conditions. The highest accuracy, over 95%, was achieved in task B2, where we used data from multiple camera positions and rotational speeds. This is part of our key findings that incorporating data from different viewpoints enhances the model's ability, and our model is robust against different rotating speeds. To summarize our key contributions, our model was able to accurately detect machine faults, to be specific, the bearing condition in a rotating machine. And we used the event-based camera, a non-contact sensor. It is flexible and data efficient. We perform multi-angle setup and cover diverse operating scenarios. Therefore, our methodology demonstrates strong generalization capabilities. In conclusion, this work is among the first to apply dynamic vision data in machine condition monitoring, offering a potential new avenue for non-contact and real-time industrial diagnosis. And that's all for our introduction to our work. If you are interested in our work or have any questions, feel free to contact us. Thank you very much.